Hi guys, Professor Stevens here again. We're going to look at another question together from the 5.2 assignment. Based on a poll, 50% of adults believe in reincarnation. Assume that 6 adults are randomly selected and find the indicated probability. Complete parts A through D below. So we have 4 parts coming up here, and the first one, A, says, what is the probability that exactly 5 of the selected adults believe in reincarnation? So the easiest thing to do with a question that gives you a percentage that looks like a success rate is to consider whether it qualifies as a binomial random variable, or if you can set it up so that you can use the binomial probability distribution function. All right, so again, the requirements, I have them on the previous. This is the example, the spreadsheet for the example I did in the previous video. So let's just focus in on the requirements for a random variable. If x is a binomial random variable, then we'll have a fixed number of trials, we'll have only 2 outcomes per trial, we'll have independent trials, and we'll have constant probability. Okay, so requirements for a binomial random variable. Where x counts successes. Okay, so then 1. Do we have a fixed number of trials? Yeah, let's see. It says, based on a poll, 50% of adults believe in reincarnation. Assume that 6 adults are randomly selected, so that's n equals 6. 2. We need only 2 outcomes per trial. So in each trial, what is the question that's going to be asked, or what is being tried? We're going to do a poll, and we're going to try this poll on 6 people. And every time we ask an adult this question, we will have a 50% chance that they will say they believe in reincarnation. Okay, so then we do seem to have only 2 possible outcomes, which would simplify to only 2 outcomes per trial, yes or no, when they say they believe in reincarnation or they don't. 3 is independent events. So if the first person says they believe in reincarnation, it doesn't mean that the next person is going to be more likely to say they do, and it also doesn't mean they're going to be less likely to say that they do. So these are independent events. Successive probabilities unaffected. Okay, and then 4, constant probability of success each trial. Okay, so the probability of success, which is the probability that they believe in reincarnation, or the probability that they say yes, is 0.5, 50%. And that will be the same every time you ask someone. So we have N, P, N, P, and Q. We also want a place for X. So N is 6 adults. We'll skip over X for now. P is 0.5. Then Q, of course, is also 0.5. Since there's only 2 possibilities, they have to be complementary, meaning they have to add up to 1. So the probability of failure is 1 minus the probability of success. Okay, so we're doing well so far. Based on a poll, 50% of adults believe in reincarnation. Assume that 6 adults are randomly selected and find, here we go, here's the objective, find the indicated probability. What is the probability that exactly 5, okay, so that means X is 5. So we're being asked to find P of X being exactly 5. Right, and we can do that with the binomial probability formula. In Excel, it's binom.distribution. It first wants the number of successes, which is 5, then the number of trials, which is 6, then the probability of success. It'll automatically figure out Q for us by doing 1 minus P, and then whether we want it to be cumulative or not, and the fact that it says exactly 5, we will not want this to be cumulative. So you can either double click false or just choose 0, which means no for cumulative. There we go. All right, so the answer appears to be 0.0938. So it's to 3 decimal places. Well, usually you go to 3 significant digits for probabilities, but this is actually instructing us to round to exactly 3 decimal places. So I'm going to put this out at 4, and we got it. Excellent. Now let me show you how to calculate that with the formula on paper. So that would be P of X is equal, so this is the binomial probability formula, which is NCX combinations, the number of ways to get a certain number of successes in N trials, times the probability of success to the power of the number of successes you're going to have, and then times Q, which is the probability of failure, to the leftover. So if I've had X successes out of N trials, then the remaining N minus X trials would have been failures. So for this one, we're doing P of 5, so that we have 6 choose 5 ways to get 5 successes. And then we're going to multiply that times the probability of success, which is 0.5, to the power of 5 successes, and then times Q, which is also 0.5, doesn't always work out like this, and then take away 5 successes from 6 trials, and you have 1 leftover trial that's going to be a failure. So this is the number of ways. This is the probability of, this is the 5 successes in a row, and this is the probability of 1 fail. Okay, so the formula for 6C5, that's the combinations formula. Whoops. D looks like this. And then since they have the same base, it's actually easier to just write this as 0.5 to the power of 6. And that is only because we have equally likely outcomes. And then we have 6 factorial over 1 factorial, 5 factorial times 0.5 to the power of 6, which is 6 times 5 factorial over 5 factorial, which cancels these out, and then times 0.5 to the power of 6. So what we end up getting is 6 times 1 over 2 to the power of 6, and so that is 6 over 2 times 2 times 2 times 2 times 2 times 2, which is 8 times 8, because 2 cubed is 8, 8 times 8 is 64, those are both even, they reduce to 3 and 32, and you know, that was kind of a longer way to do it, but if you had to show it out, you could do that. Now, I also want to show you that I can verify that my combinations when I have 6 items and 5 successes, I will have 6 possible ways to get that. So what I just did there is I used Excel's combinations function to verify this part of my calculation. the 6 factorial over 6 minus 5 factorial, 5 factorial. So the 6c5, which came out to be 6. I can also do the whole calculation is 6 times 0.5 to the power of 6, or I could have done 6 times 0.5 to the power of 5 successes times times 0.5 to the power of 1 success, or like I said before, it was, what did I say in my calculation? 3 over 32. Yeah. Okay, so just different ways of getting it. It's sometimes something I ask you to do is show how the formula works out on paper. I don't really care about all this stuff where you really show every little step. I don't care about all that so much. This part I like right here, showing how to cancel out the factorial. That's definitely something you should try to do. But if you can get, like, you know, at least let me see that you used the formula, the general formula, and that you knew where to place the n, the x, the p, all that stuff, knowing how to use the formula. And then you can use Excel to help you with those calculations. And then we can always, what do? We use binom.distribution to get the original answer. So it's not the kind of thing that you should get wrong. If you get the wrong answer and you're checking it with binom.distribution, you should catch your mistakes pretty easily. So just don't be in a rush. Make sure you pay attention to whether or not your answer checks out. Okay, so let's go back to the question. Okay, so what is the probability that all of the selected adults believe in reincarnation? Oh, all of them? Well, all of them would mean exactly 6, right? So I can just do P of X equals 6, which is binom dot distribution. Number of successes would be 6. Number of trials would be 6. Probability of success is 0.5. And do we want cumulative? No. So there's the answer for that. To 3 places, 0.016. And what is the probability that at least 5? Well, that's a very different question, and this is the fun part, because now I get to sell you on why you might want to build a probability distribution. But before I do that, I'm going to do it the easy way. The probability of at least 5, okay, that is like saying x is at least, right? So equal to 5 or more. Oh, that's not so hard. I was thinking it was 5 or fewer, but if it's 5 or more, that's easy, right? That is the same thing as saying the probability of 5 or 6, since we're only doing 6 questionnaires. So we just have to add up the probability of 5, exactly 5, plus the probability of exactly 6. So we can do that. That's no problem, because we already have those answers right here and here. So we just need to add them up. Right? So let's do that. So we're going to add up the probability of 5 and the probability of 6. And there's our answer to 3 decimal places is 0.109. Cool. Okay, and if 6 adults are randomly selected, is 5 significantly high? Okay, so if 5 is significantly high, then 6 also is significantly high. So we want to see if the probability of 5 or 6 successes is rare. If it's rare to get 5 or 6 successes, then we'll say that 5 is significantly high. So the rare event rule, we're looking at this probability right here. And the rare event rule says we consider an event to be rare if the probability is less than 5%. So this is less than or equal to 5%. So we can see that we have 0.109, which is closer to 10% or 11%, which is not rare. So I would say no, it's not that unusual or unlikely to get either 5 successes or even 6 successes. So 5 is not a significantly high number of people to believe in reincarnation. So it's either going to be A or C, where they both say no, but let's read them carefully. Either A, no, because the probability that 5 or more of the selected adults believe in reincarnation is greater than 0.05. 5 or more. Okay, so read that again. No, because the probability that 5 or more. That's good. I think that's the one we want right there, because we did need to look at the probability not just of exactly 5, but also of more than 5. The part C, or answer C, says no, because the probability that 5 or more. Oh, that's no different. Those look, in fact, I could have just seen these look exactly like all the way up to, oh, here we go. A greater or a less. So it's A, because our probability is greater than 0.05. I was thinking of another type of question that comes up in some of the, it's another homework question that you'll probably run into, where the distinction is, are you looking at the probability of exactly 5 successes to determine if it's significantly high, or should you be looking at the probability of 5 or more? There are actually some questions that show up in your assignments that are focused on that, but this one is really just focused on the fact that we want a probability that is smaller than 5% if we're going to call it rare. So here, because our probability is greater than 5%, we'll say no. Alright, so that's that kind of question, and there's other ones like it. Based on a poll among adults who regret getting tattoos, 13% say they were too young when they got their tattoos. Assume that 8 adults who regret getting tattoos are randomly selected and find the indicated probability. Find the probability that none of the selected adults say they were too young to get tattoos. Okay, so last time I just did each part individually, but this time I'm going to show you how to do it with constructing a probability distribution, like the entire table. And this is question 5.2.28-T. Okay, so I'm going to do my N, my P, and my X, or actually I'll do N. Does it matter? I've been doing it like this, so I'll keep doing it like that. And then I'm going to have X is the number of adults who say they regret getting tattooed. And then so X is going to be, since I'm going to be asking 8 adults, and X can be 0 adults say they regret it, or just 1 person could say it, or 2 people could, and all the way up to 8. And then my probability of X, since it's a yes or no question, and I have a fixed number of trials, and they're independent events, the probability of success, 13% say they were too young. Okay, so let's go with 0.13 as our probability of success. Someone saying they regret it. And then Q is 1 minus P. And I don't really need X to be here because I've got all my X's down here. So I'm going to just remove that. Oops, didn't mean to go that far. There. Okay. And then since this is binomial, I can do binom. Oopsie. Got my keys and fingers in the wrong place on the keyboard. Binom dot distribution with the number of trials x. I meant to say the number of successes, x. So for 0 successes, and then 8 trials, probability of success. Oh, let me do a couple things too. I want my n to be absolute reference, so it won't drag down. Always referring to that cell, not the one under it. Then the probability of success, also absolute. And then cumulative, no, I want this to be exact for each one of these. And then I'll just give myself some more places. I see the scientific notation here, which is bugging me, so I'm going to go out to like 9 decimal places. Maybe I shouldn't do that. Maybe I should leave it as it is. Never mind, I'm going to leave it as it is. It's fine. But this is actually... No, I'm not going to leave it. I'm going to do it all the way out because I feel like you guys need to see it. Okay, so I'm going to go to like 10 places. Okay, that looks better. Because now you can see more clearly that they are all each between 0 and 1. And if I've done it correctly, this should sum to 1. And it does. Excellent. Okay, so that's my x times p of x. And now, why did I do that? Because it's asking me parts that I can get from right here. So see how it says find the probability that none of the selected adults say they were too young. So that's this answer right here for the probability that 0 people said yes to 4 decimal places. That's 0.3282. And then find the probability that exactly 1, that would be this answer right here. So that's 0.3923. Okay, find the probability that the number of selected adults saying they were too young is 0 or 1. So that would be adding these two together, which is easy to do here. So P of 0 or 1 is the sum of these. So that would be 0.7206 to 4 decimal places. Okay. And then if we randomly select 8 adults, is 1 a significantly low number who say they were too young? Okay, so again, just like it worked when we were doing 5 being significantly high, we looked at the probability of 5 or 6 or 7 or 8. If 1 is low, then 0 is low. So we are interested in the cumulative probability of either 0 or 1. So looking at this, we were looking for less than 0.05 probability, less than or equal, so no, it's not, 1 is not a significantly low number, because the probability that at most one or fewer of the selected adults say they were too young is greater. Okay. Something else interesting too is cumulative probability. So I'm going to show you how to do, this part isn't so important, but just if you ever want to do symbols, you can insert them. I went to the insert menu and then went to symbol. Less than or equal to a certain number of successes. So that's cumulative, right? Like here it's exactly x, like this, that actually means the same thing. When it's written like that, it actually means like this, that it's exactly equal, right, to a certain x value. So cumulative is like you take, like for this one, less than or equal to 1 would be both of those. This one, less than or equal to 2 would be all these, and so on. But you can do that with the binom distribution, again with the number of successes The number of trials, absolute. The probability of success, absolute. And cumulative this time we'll say yes. So that's going to give you the probability of X or fewer. You see how I did it? And I'll just do it for us. You see how these all match? The ones I did myself, I did them by hand. I did the sum of 3 or fewer. Sum of 4 or fewer. Oops. Hit something funny. Here we go. And you can see how they're all matching up here. So the binom dot distribution formula, when you choose true, gives you cumulative probabilities less than or equal. So it's cumulative from the left. So I'm just going to clear this out and I'll move these over. All right, so cool, right? Because now look at this. You remember how our answer down here is 0.702 for part C. And right here you can see when I added these two together, or if I use the cumulative option for the binom distribution, that gives me the answer directly. So that can be useful. It can be useful for these questions. This is a good one too. I'll do this one maybe quickly. This video might be getting a little long. Assume that different groups of couples use a particular method of gender selection and each couple gives birth to one baby. This method is designed to increase the likelihood that each baby will be a girl. I can't do this. I have to stop it now. Sorry, I have to go home. I just realized what time it is. But that was fun. I hope it was helpful, and I will see you in class.